Okay. So first of all, let me ask you, has anyone noticed how the date is special today? I was just writing the date for the lecture and I noticed that it was very special.
Palindromic date.
Yeah, it is a palindrome today, after a long time. Anyway, okay, so let's see. So now we know the Hartree-Fock equation. We know how to solve it. We've talked a little bit about how to choose a basis in which to represent my orbitals. But there is much more to be said about that. We will do that on Monday about the basis sets. But today we will talk a little bit about how expensive it is and which parts of the computation are most expensive and how we deal with it. So there are lots of little things that need to be said. So I will try to keep it as organized as possible, but it will still probably be a little bit haphazard. Okay. So the first thing that I wanted to say was that what is the first thing that you do? The first thing is that you set the nuclear coordinates. Then you choose a basis set. The basis sets are atom specific. I've mentioned this many times. They are atom specific and there are different qualities. So you choose a quality that is most suitable for your computation. And the functional expression of these basis sets are normally Gaussian functions, because integrating Gaussian functions, there are lots of numerical tricks which make it efficient. So that is the reason Gaussian functions are used. Ideally, they should have been Slater type orbitals. So Slater type orbitals are orbitals which look like the hydrogen atom orbitals, which come from an exact solution of the Schrodinger equation. Okay, but we will talk about that much more on Monday. So just hold on there. Let's just say we now have a suitable basis function. Now the next step. So after, let's put them down. So we now have nuclear coordinates. And we have basis sets for each atom. Then the next step is to evaluate the integrals. So what are the integrals that are involved in my Hartree-Fock computation? My equation is Fc equal to Sc epsilon. So I have the Fock matrix, which I need to construct. There is the overlap matrix, which I need to construct. And overlap matrix in AO basis. And inside the Fock matrix, we have two parts. We have the one electron part, so Hij, let's say, or H core mu nu. I think that's the notation that we used, H core mu nu. And we have the two body parts, so J mu. Let's see how to say it, J mu nu. Or let's just say integrals of the type mu, nu, gamma, delta. Okay. So if this was an MO basis, I could have easily said which one is Coulomb and which one is exchange. Okay, that is why I stumbled when I was trying to write this. But in the AO basis, we just need all of them. Okay, there is no distinction between the Coulomb and the exchange. Anyway, so these are the integrals that we need to construct. So there are three types, 1, 2, and 3. Now you see the S and the H core mu nu, these are two index quantities. And this Mulligan integral, that is a 4 index quantity. So let's look at how expensive it will be to compute this, or the number of elements that I need to compute. So let's say I have a basis set size k. This means that I have a total of k basis functions for my molecule, which is the sum of the basis set sizes of all the atoms. Then my H mu nu and S mu nu, the total number of elements is k squared. And the total number of elements for mu nu gamma delta, the two body integrals, they are k to the power 4, roughly speaking. Now, this is not quite accurate because there are some symmetries which we can exploit. So H mu nu and S mu nu are both symmetric matrices. So basically, it's not k squared, but k into k plus 1 by 2. That is the number of elements we need to store. And in case of the two body integrals, because of the symmetry of the Mulligan integrals, which we did several classes before, it has an 8-fold symmetry. So you need to store k to the power 4 by 8 number of integrals. But even then, let's say I have 100 basis functions, so 10 to the power 2, then the one body integral, each of them is about 5,000 numbers, and the two body integrals, they are already, so they would become so k equal to 100, then k into k plus 1 by 2 is roughly 10,000 by 2, which is 5,000, and k to the power 4 by 8, that is equal to 10 to the power 8 by 8. So that is much, much more than a million. So this is very, very large. So you have millions of integrals. So now it is, so with this quick back of the envelope calculation, you can see that your integrals, the two electron integrals or the 4 index quantities, will dominate your storage. So what you need to store before you can start the Hartree calculation. So most of the effort is directed towards optimizing this. So even after you have, so there are some more symmetries that you can exploit. So here we have used the index symmetry of the Mulligan integral to reduce it from k to the power 4 to k to the power 4 by 8. If your molecule has some symmetries, like point group symmetries, then you can do away with some more integrals and reduce this number further. So that is also exploited. So, and the third thing that you can do is, if the two basis functions are spatially separated a lot and they have very small overlap, then the integrals also turn out to be almost 0. So what is done is that only non-zero two-body integrals are stored, and a list of the indices are maintained. So instead of computing all the two-body integrals, only specific non-zero ones are, well, the storage at least is only for the non-zero ones. For the computation, you can only not compute the ones which are analytically zero. So the ones decided by Mulligan symmetry and the ones decided by molecular symmetry. And if your integral is very small because of spatial separation, you have to compute it, see, and then discard it. So that is the thing. And the computation of these 4 index quantities also dominates the computation cost of Hartree-Fock. That is one thing. Also, if so, let's talk a little bit more also about the code. So after you have written these integrals, if you have written them to file, then the read-write of these integrals also dominates your computation. So then what happens is the actual calculation of the integral may become cheaper than reading from file every time you need it. So there are some procedures called direct Scf procedures where you always compute the integral. You never store it. And many years and many have been dedicated by many scientists to optimize these things. And now you have highly optimized Hartree-Fock implementation. So you can be sure that if you implement it yourself, which is as such not difficult, but you will encounter a lot of computational difficulties in terms of managing storage, speed, etc. And also some numerical instability. So these things have been optimized over many years. So it's not like you can just sit down and do it at any point of time. So the next point is, remember so this is, let's say, bullet point 1. So this is, let's say, bullet point 1. Or okay, I've said this is 3. So let's call this 4. So if you want to start any iteration, you need to start with a guess. To guess something, whatever quantity you are iterating. In our case, our Fock matrix is a function of the density matrix, which we spoke about in the last class. The density matrix is nothing but 2C star, where C is the matrix of coefficients of the molecular orbitals, and P is a concise representation of that. Okay. So what you need to guess is, of course, then the density matrix. Now inside the Fock matrix expression, the density matrix occurs in both the integrals. So my Fock operator, that has a one-body part and it has a two-body part. And because the two-body part involves the molecular orbitals, the Fock operator becomes dependent on the MO coefficients and hence the density matrix. The Fock integrals, on the other hand, that is F mu nu, is mu F nu. So this is always so this is in the atomic orbital basis. So then also mu H nu, this is independent of So if you start with a guess of, if you start with a guess that P is equal to 0, then your guess Fock matrix will be the expectation value of the one electron part of the Fock operator with respect to the basis function. So this is not a bad guess at all. So this is something that is available in most codes, that you start with just the one electron part, and this is normally called guess it, like the guess is H core. So this is what you say when you start with just the one electron part of the Fock matrix, and then once you solve the Hartree-Fock equation, the canonical Hartree-Fock equation, you get the MO coefficient C, you construct P, and then you construct everything. Then you will evaluate the two-body part as well. Okay. So notice that when I talk about the Coulomb exchange part of the Fock operator, I say two-body part or two-electron part. While for the integrals, I say two index integral or four index integral. So that can get a bit confusing at times. So for the operators, you have the one electron, two electron, and for the integrals, it's two index or four index. Okay. Just wanted to point that out. Then this is, and then once you've guessed this density, you can continue. So what are the other guesses available? So this is the most obvious guess. Another guess is what is called the Huckel guess. So the Huckel model is a sort of intuitive model for molecular orbitals of molecules. So you must have encountered Huckel theory with respect to aromatic molecules, like conjugated polyenes or benzene and pentacene, etc. So, and the Huckel model sort of tells you about how the pi electrons interact in a molecule. The sigma electrons just give the molecule a shape. So it's like a simplified model. And for molecules that contain pi electrons, these electrons dominate the chemistry of these molecules. So the Huckel model turned out to be quite effective. So this same sort of intuitive model can be used mathematically to get some guess molecular orbitals. So you are guessing the coefficients C, the zeroth iteration, from an intuitive model which sometimes also has empirical parameters. Okay. So there are sometimes some empirical parameters in this model as well. I will not go into great detail of this model, but this is implemented in almost all packages, and it is the most effective guess to start with, which is called the Huckel guess. Okay, so you guess some sort of coefficient C from this intuitive model. You construct then P0 from the C zeros, and you continue. You can also use as a guess the MO coefficients from an earlier calculation. So an earlier calculation meaning what? Maybe it can be a calculation in a different at a different nuclear geometry. You can use the MO from that as a guess for a new geometry. You can also guess it from or in a different basis set. Now, this may look a bit counterintuitive because if you have a different basis set, then the atomic orbitals you are referring to are already different. So the MO person, so what I mean is, say you have the coefficients in a basis B and a coefficient in a basis B prime, then AO by MO, this is also AO by MO, so number of AO by number of MO, but this number and this number are different because the two basis sets are different. But this is also done. What is done is similar atomic orbitals, you take the coefficients and whatever is missing in one basis set and is present in the other, you just put a 0 for that coefficient. So this can also be done and is implemented in some packages, not in all, but it can be done. The MO, you can also guess the MO coefficients from a different molecule with similar structure but same basis. So this can also be done. So the guess can basically be anything that is reasonable. And it can well be that your calculation converges with one guess, but it doesn't converge with another. Or it converges in 10 iterations with one guess, but it takes 200 in another. So these are all matters of tweaking things and seeing what works best for your system. So this is about the guesses. So the guess must be on the density matrix, but if it is easier to guess the coefficient, like when you're using the Huckel model, you can do that and construct your guess density and feed it in. Okay. And one more point with regard to, so then now point number 5. So of course, solving FC equal to SCE involves matrix multiplications. Now these also need to be fast, so your coding has to be good, and the main reason why this can be slow is because of what is called cache misses or memory misses. So how you organize your matrices is very important, and how easily you can access them. So that is what determines the speed of these matrix multiplications. And also, but for Hartree-Fock in particular, the matrix multiplications are typically less time consuming than the computation of the computation of the new Fock matrices every time. So constructing FP for nth iteration is typically more expensive than the matrix multiplications involved in the Hartree-Fock equation. So this is just good to know. So if your code is slow, you must be sure that your Fock matrix construction, especially the the 2 electron part or the 4 index quantity part is done well before you start optimizing the actual equation. So that is that. So now I've more or less covered the different aspects of the computation. Now let's say we are done with the computation. We will shift gear a little bit. So we have obtained our Hartree-Fock wave function psi naught. And getting the energy from it is a simple byproduct. So we have also computed E0, which is my Hartree-Fock energy. So what more can I find out? As you know from quantum mechanics, the wave function is supposed to tell me everything about the system. So in principle, I should be able to find out all properties of my molecule from psi naught. And that is indeed true. So what you need to do, as you know, is you need to take the expectation value of various operators, and that will give you some property. Say property O. And if I take, give me another letter. So let's see, zeta, some other operator, I will get another property, let's say Z. The different properties will be obtained by taking expectation values of different operators. Now, the form of these operators is something you must know from physics. So normally this comes directly from classical physics. And then you need to evaluate new integrals. But now I'll tell you one thing. So this wave, so what you get out of the Hartree-Fock equation after you solve it is a final optimized. So what I have is a optimized P mu nu. So I have an optimized density matrix. And perhaps, and along with that, I have the MO coefficients as well. But I do not have a functional form for the wave function. And neither do I have the psi naught on a grid. So psi naught, how is it represented? So psi naught, we have been saying, is a determinant of spin orbitals. Okay. Now my individual spin orbitals are the molecular orbitals multiplied by the spin functions. But we don't know any explicit form for the spin functions. We also don't know the functional form of the orbital. We only have the coefficients in a basis. So there is no analytical way of writing this determinant from the density matrix and the coefficient matrix that you have obtained. So I don't really have this. Okay. And of course, I certainly don't have a functional form for this. So something like f of r, this also I don't have. The other option was to have it on a grid. So as, let's say, a grid function. This is possible, but it is very expensive. So this is what I have, and now I want to carry out an integration. Can I do it? So if I had a functional form, I could definitely integrate any operator. If I had it on a grid, maybe then also, provided my operators are suitable, I could have done it. But if I don't have the wave function explicitly at all, can I do it? Actually, it turns out that it is more simple than we are than doing it with the wave function. So let's see why. So let's see, let's say I have a 1 electron operator, theta 1. So let's say I want to do theta 1 psi 0. This is a 1 electron operator. Okay. Then I have Slater's rules. So what does Slater's rule tell me? Slater rule tells me that if it is a 1 electron operator and psi naught is a determinant with spatial orbitals, multiplied with spin orbitals. So here we are again talking about a restricted closed shell determinant. Which means the number of alpha and number of beta are the same. My determinant will have n columns and n rows, that is the total number of electrons, and there will be n by 2 alpha functions or alpha spin orbitals and n by 2 beta spin orbitals. So the determinant always has to be written as a spin orbital determinant. So writing something like psi 1 1, psi 1 2, psi 2, where psi is spatial, this is wrong. You cannot do this. Okay. To be written with spin orbitals. So then you have this psi 1 1, psi 1, and psi, and you can write them as maybe psi 1 bar, then psi 2 bar, etc. That would be correct. Okay. So you can't write a determinant with spatial orbitals, remember that. But when I say that it is a restricted closed shell determinant, then after I open it in terms of spin orbitals and I evaluate the matrix element with Slater's rules, the expression that I get can be reduced to a sum over spatial integrals. That can be done. And these are the spatial orbitals that I have obtained after optimization. And this is small h. This is the one individual of electron 1. So theta 1 is, let's say, a sum of H1. So here H is not the Hamiltonian. This is the 1 electron part of whatever property operator that I am computing. And here the property operator itself is 1 electron. So you only have 1 electron part. Is it confusing you? Am I confusing you? It is a little bit confusing. I mean, so this is a 1 electron operator overall, but one at a time. So you have a sum. You can have a sum of over all the electrons, just like the Hamiltonian. So this could have been theta 1 part of the Hamiltonian, like we were talking about earlier. but it can be a different operator as well. Okay, but the Slater's rule still holds, and you get this expression. Now, if I expand every MO in terms of the coefficient matrix, so this will actually turn out, there will be a 2 here. Okay, and then I expand the MOs in terms of the AOs, and I will get to C star C. I'm not writing all the indices. And mu H nu, but this is the AO basis, and then I sum this over A like we have always been doing. And I get sum mu nu, P mu nu, or P nu mu. It will turn out to be P mu mu, mu H nu. So this is what it will turn out to be. So once I compute the property integrals in my AO basis, then simply having my optimized density matrix is enough to tell me the expectation value of the Hartree-Fock wave function with respect to n for any property operator. Is that clear? So I did not need a representation of my wave function explicitly, again, because we have Slater's rule is our saving grace here. We can apply it here, and then the MO expansion shows me that optimized density matrix, the property integrals in AO basis. Okay. So what sort of operators can we expect? The dipole moment. Okay. For electrons, in a quantum mechanical context, the mu operator is written as a minus, because of the charge of the electron, sum over all the electrons in the system, and the sum over from I equal to 1 to n being the number of electrons in the system, of the position of every electron. So Ri. So this is the classical expression, general expression, and this is the quantum mechanical equivalent for electrons. Fine. And in addition to this, you have a nuclear part, because the nuclei also have charges, and that is the atomic number of every atom, Za, multiplied by the location of these nuclei. Now, since we are using the Born-Oppenheimer approximation, the RAs are fixed vectors, ZAs are fixed. So this is simply a number. So you don't need any integration to evaluate this part. So you can say that so this is the dipole operator, and the dipole moment vector is then an expectation value of the dipole moment operator, and the integral that you need to evaluate is then minus sum over Ri psi 0. This is what you need to evaluate. And again, because Ri is a one electron operator, other electron. So Slater's rule tells me that this is equal to minus of mu r mu. Okay. And knowing the functional forms of mu and nu, so these are functions, let's say Gaussian or Slater type orbitals, then you have to simply numerically evaluate an integral with an r in the middle. So you will have some function star, r in the middle, some other function star, and you have to figure out a way to numerically integrate this. And once you have the property integrals in the AO basis, and you have done your Hartree-Fock calculation to get the optimized density, you can simply do this multiplication. Okay. So that is clear, I hope. That once you have P nu mu, you can find the properties of the system using it. Now, the other thing that you can find out after you know psi 0 is you can try to analyze the charges on the various atoms involved. So why do you want to do this? So chemists have this intuitive idea of electronegativity and partial charges. So for example, if you have, let's say, CO molecule, you might wonder if it is C delta plus O delta minus or C delta minus O delta plus. So chemists want to know this. So then again, you have to have some theoretical quantities which will give you some numbers for these intuitive ideas. And so one such thing is population. Analysis. And what is population analysis exactly? It is sort of the number of electrons to be associated with a given atom or nucleus in a molecule. So this is to correspond with intuitive chemical ideas, we can compute some quantities which tell us the number of electrons associated with various parts of a molecule. Now, Because as you know, quantum mechanics is a probability of being everywhere. There is no fixed distribution. But if you sort of want to know, have a rough idea of where the electrons are, or which part of the molecule would behave as if it has a positive charge, so things like this, then you can compute quantities, various quantities, and all of them are put under population analysis. And there are many types of population analysis. So you can have, there are various types. So one is called Mulligan population analysis. One is called Lovedean population analysis. And there are others. I can't remember any other one at the moment, but there are definitely more. Okay. So let's see what it is all about. So what we so remember, we had defined a charge density function, which was a sum over all the atomic orbitals of the density matrix P mu nu, and then phi nu star, where the phi nu and phi nu are the atomic orbital bases, right? And we also saw a property of the density matrix, or the wave function. We can write it like that as well. So if you sum the number of, so for a finite volume element dr, if you sum the contributions of all the molecular orbitals and you integrate it over all of space, you will get all the electrons n. So I'm integrating every molecular orbital over all space. So from normalization also, so if you're talking in terms of mathematics, then from normalization also, this will give you the total number of electrons, n. Okay. So now if I put in the basis expansion of psi A into this expression, so if I put in psi A equal to some mu Ca C mu A phi mu, if I put this MO expansion back into this expression, then you will see that n becomes equal to sum over mu nu P mu nu S nu mu. Okay. So what is this? So this is sum over mu. So if I do the sum over nu, just nu, then this is a matrix multiplication of P and S. So these are matrices. And then you have the mu mu element. So n is then the trace of PS. Okay. Then if you look at the expression here, then for every atomic orbital mu or phi mu, you can have a fraction of the electrons belonging to it. So PS mu mu represents a fraction of the total number of electrons which come from phi mu. And phi mu, remember, is an atomic orbital. So it belongs to one particular atom. So you can interpret PS mu mu as the number of electrons belonging to phi mu, which is an atomic orbital centered on some atom A. So let's say it's a particular atomic orbital. Now, if I sum over all the atomic orbitals belonging to a particular atom. So these are the basic functions. So remember, they were atom specific. So I know which atomic orbitals belong to which atom. So if I sum all of them which belong to the same atom, and I sum these belonging to, in the molecule belonging to atom A, and then minus this Na. So Za minus some mu belonging to, and this is called Mulligan population. Okay. Now notice, now we will see why this is not such a rigorous concept. So see, the number of electrons, the trace of PS, and the trace of AB is equal to trace of BA. Right? So, if I modify my expression to S trace of S to the power alpha, PS to the power 1 minus alpha, this is exactly the same as trace of S to the power 1 minus alpha S alpha P, which is equal to trace which is equal to trace of PS. So I could, and I can choose any value for alpha, and it would still, and I would still satisfy N is equal to sum over mu S to the power alpha P S to the power 1 minus alpha mu mu. So this can also be interpreted as some quantity which tells me the number of electrons belonging to atomic orbital phi mu. It can be anything. And in fact, people did realize this it could be anything. And another sort of population analysis was done where alpha is chosen to be half. And then the partial charge on an atom A is its nuclear charge minus sum of all atomic orbitals belonging to A, s to the power half, p s to the power half mu mu. And this is then called the Lovedean population analysis. Now, there are many reasons for choosing one over the other, or when you are looking for a particular type of molecule, or when you're comparing molecules. Okay, so personally, I have never used population analysis a lot, but if you're doing a lot of chemistry and you're trying to understand reaction mechanisms, etc., you will often be doing population analysis, but it is good to keep in mind that these are not rigorous concepts. Quantum mechanics does not tell you how many electrons reside on one atom. These expressions are not rigorous. You can have alternative expressions, and it may well be that you get contradictory answers. So it's good to keep it in mind, but largely they are useful, so people use it. Okay, so that finishes our discussion about Hartree-Fock theory. So you can stop the recording for today.